Hi, I'm Philip Brown. I'm an assistant professor of computer science at the University of Colorado, Colorado Springs, and I'd like to talk to you about some ideas I've had lately with respect to mixed autonomy in transportation networks. So at a high level, I'm interested in what I call sociotechnical systems. That is, it's an engineered system coupled with a social system in such a way that the performance of the overall system can't be blamed on just one or the other of the engineered and the social piece. So we see a huge variety of these in smart infrastructure and cryptocurrencies, the sharing economy, e-commerce, and the list goes on and on and on. And the question for the engineer in these contexts is, how do you design the engineered piece when it can't really be separated from the social piece, and yet you can't directly influence the behavior in the social piece? So to kind of study ideas surrounding this, we're going to look at the paradigm of heterogeneous behavior design in game theoretic systems, and in particular the picture you should have in your head is transportation networks with mixed autonomy. So in other words, we're thinking about systems like what we have right now, and like what we're moving into for more and more as time goes on, in which most of the drivers on the road are humans and have their own objectives, but some of the drivers on the road are autonomous. Right? More and more we have algorithms driving these self-driving cars, and the question is, if the engineer can design the behavior of a subset of these agents, a subset of these vehicles, what should the engineer do? And so one very simple, conceptually simple approach that the engineer could take is something that I call altruism. So altruism I'm going to define today as a behavior policy that means what I'll do is I'll look at others' choices, and then I'll do the best for the system that I can. So altruism is like a personal utilitarian objective. So an altruistic self-driving car essentially attempts to optimize the performance of the transportation network the best that it personally can. And in the context of the models we're going to look at today in these nonatomic congestion games, it's known that if all the vehicles are altruistic, so if we have control over the decision policies of every vehicle, then optimal behavior emerges as Nash equilibria of the behavior of the altruistic vehicles. However, it's also known that if only some of the vehicles are altruistic, that can be worse than if none are altruistic. So partial altruism or heterogeneous altruism can be worse than homogeneous selfishness. And so what we want to do today is come up with some upper bounds on how much harm altruism can cause in these kinds of environments. So to do that, we're going to look at a model of a nonatomic congestion game. And so the way this model works is we have a transportation network with some sources and some destinations, and we have some traffic that has to use that network. And so the traffic is a blob. So we think of it as a continuum of infinitesimally small agents, each with its own decision to make. And then we'll characterize the costs of those decisions in terms of the delays that they cause on the roads. So the delay on a road is going to be characterized by a latency function that takes in the amount of traffic using that road and returns the delay. And so in this network, if we have one unit of traffic, it's not difficult to show that if we split half the traffic on the top and half the traffic on the bottom, that minimizes the average delay experienced by traffic. And so here we have half a unit of traffic with a delay of a half of a unit of traffic with a delay of 1, and so the total delay is 3/4. And this is optimal with respect to this metric that we call the total delay. The issue is that it's not socially stable. So any agent using that lower path has a delay larger than it would need to be, and so there's an incentive to switch, and if all agents switch, we arrive at something called a Nash flow, which is a routing profile, so it's an assignment of traffic to the links, such that no agent has an incentive to deviate. And so here the Nash flow now has a total delay of 1 because all the agents have a delay of 1. And so the fundamental thing that drives this inefficiency of selfishness is congestion externalities. So the way a congestion externality works is something like this. So you can think of the total contribution to system cost of each driver as the delay they experience themselves, plus the delay they impose on others. So this is the marginal delay, the external delay. And so in this particular network with these particular cost functions, that just looks like the delay plus the delay. And in other kinds of cost functions, it's going to look a little bit different. But there's been a lot of work that's focused on what happens if we just modify the cost functions of the agents to incorporate this imposed delay. And so it's worth mentioning that this is equivalent to saying let's allow the cost functions of the agents to be equal to the gradient of the system cost function. So it turns out, if we do that, that all Nash equilibria end up being optimal. And so we're going to call cost functions that look like this, like delay plus marginal delay, we're going to call those altruistic cost functions. And so it's known, and this is called the price of anarchy, that if all agents are selfish, that we have inefficient routing. It's also known that if all agents are altruistic, we have optimal routing. And so the question that we have today is what happens if we have mixed altruism? What if only a subset of the agents are altruistic? And so to study this, I'm going to pose the network a little bit more formally here, though the full details you'll have to find in the paper. And so here we have a network with sources and destinations and nodes and edges. And we characterize the fraction of the total traffic that is altruistic by alpha. So humans, or selfish agents, have cost functions that are just equal to the latency functions on the edges, and we'll assume that these are convex and continuously differentiable and non-decreasing just to make the math go through nicely, but these are relatively standard assumptions. And then the altruistic agents have cost functions that look like this, that are equal to the marginal costs. So the delay of an edge plus the external delay of the edge, the delay an individual imposes on others. And then we'll call a flow, or an assignment of traffic to the paths, we'll call this a Nash flow if it satisfies these two conditions. First, if humans are using a path, and when I say humans, I mean that interchangeably with selfish agents using a path. So if humans are using path P, then that path has minimal delay. And if altruists are using a path Q, then that path Q has minimal marginal cost, minimal marginal delay. And so this is the standard definition of a Nash flow that we'll employ from here on out. And we're going to measure the cost of a particular routing profile with the total latency. So the total latency is the expression you see above. It's just the sum, essentially the sum of all delays experienced by all agents. And I'll write L Nash of alpha to say the total latency of a Nash flow when an alpha fraction of the traffic is altruistic. And then I'll quantify the harm of altruism relative to selfishness with the perversity index. So that's the expression on the bottom of the screen. And so what this does is it says we're going to take the ratio of the Nash cost with an alpha fraction of altruistic traffic and divide that by the Nash cost of a Nash flow with no altruism. So this will exactly quantify how much worse things can be when there's an alpha fraction of altruistic traffic relative to selfishness. So the main goal is identify the worst case perversity index for a subclass of networks. And so I'm going to just stash that expression up top and then give you the main result, and I'll explain a little bit about what it says and then wrap up. So our main theorem says that on every series parallel network, and I can explain series parallel network in a moment, that has polynomial latency functions with degree no more than p, then the perversity index is no more than this expression, this extraordinarily simple expression for any alpha, for any fraction of altruistic traffic. So it turns out that this expression is tight, and it is made tight precisely when alpha equals 1/2. And so we actually can plot in a generic way exactly what the perversity index looks like in worst case for any alpha. And it just looks like this. So on the very far left-hand corner of the graph, alpha is 0. And so what that means is that there's no altruistic traffic. And in this case, we're just talking about selfish flows, right? And a selfish flow is never worse than a selfish flow, is what this is saying. On the far right-hand side of the plot, the alpha is 1, and so that's when everybody is altruistic. And there you can see that the perversity index is 1, right? In other words, the altruism can cause no harm. But then perversity index is maximized in the middle when alpha equals 1/2. So this means that if half the traffic is altruistic, that's the worst thing that can happen potentially in terms of the harm of altruism. And so intuitively what we see here, the way this works, is that if there's not too many altruists, then they can't cause too much harm. And if there's not too many selfish people, then they can't cause too much harm. But really what boils out of this is that heterogeneity among the cost functions of the agents is really the problem, is really the thing that drives perversity in these kinds of networks. And so here, it's also worth mentioning that the perversity index for each of these peaks on these plots is worse than the price of anarchy on the corresponding class of networks. In other words, it's worse, potentially, for some people to be altruistic than it is for everybody to be selfish. And it turns out that this is actually true for all alpha. So if you pick even a very small alpha that's very close to 0, you could end up with a very high perversity index by making your cost functions very steep, and that could actually be worse than the price of anarchy on a corresponding network. So the class of examples which render this bound tight looks like this, and I don't have time to go through the full details of this, but essentially the way it works is that if the traffic is homogeneous, then you end up with this Nash flow with a total latency of 2, and homogeneous whether it's selfish or altruistic. But then if half the traffic is altruistic, you can end up with this Nash flow, where the total latency is 3. And you can make this worse by increasing the degree of your polynomial in the following way. So to wrap up, we've looked a little bit at altruism in mixed autonomy environments and in transportation networks, and we've seen that despite the fact that altruism is attractive because it is helpful in full penetration and leads to optimality with full penetration, it can be harmful if you don't have full penetration. And in fact, the worst it can be is when half the traffic is altruistic. And so our ongoing work is characterizing this risk-reward trade-off. So anytime you use altruism, trying to get the helpfulness that you would find in full penetration, you run the risk that you make things worse on some networks. So we need to understand that risk and reward, and then we need to explore general networks. And so finally, I want to thank my sponsors at the National Science Foundation, and thank all of you for your time, and I look forward to your questions. Thanks.